Hello everyone, welcome to my YouTube channel. Today in this video we are going to discuss about the stiffness modifier to be used in the analysis in ETABS according to NBC 1052020. So here in NBC 1052020 effective stiffness of crack section is mentioned in clause number 3.4 and indicated as a rational analysis shall be performed in arriving the elastic flexural and shear stiffness properties of cracked concrete and masonry elements. In the absence of such analysis, the effective stiffness of crack section will be taken from table 1. Here in the table 3.1. In the table 3.1, the component beam has flexural stiffness of 0.35, columns at 0.7, wall cracked and uncracked conditions are 0.5 and 0.8 in terms of flexural stiffness, whereas the shear stiffness is measured at 0.4 into EC into AW for all types of structural elements, and for steel element the gross stiffness values shall be used. So before going to the analysis, let me discuss about the stiffness. We know that the stiffness is the ability of the material to resist deformation when subjected to external force such as bending, compression, twisting, or torsional force, and it is the measurement of force required to cause a certain amount of deformation in the structure. So, stiffer structure deflect less under a specific load as compared to less stiff structure. We know that force F equals to K into U, where F is the force, external force, the force attracted by the structure. K is the stiffness value or stiffness properties of the structure, and U is the displacement or deformation of the structure. Here, if the value of K is higher, or if the stiffness is high, if the stiffness value is high, F equals to K into U. So if the stiffness value is high, suppose if this value is high, we see that the attracting force by the member will also be high. And if the stiffness is low, the element will attract low force. Suppose, for example, building codes have different stiffness modifier to consider the crack section. For example, if a slab has 0.25 as stiffness modifier, beam at 0.35, and the column at 0.7, it means that the slab cracks more than beam and the column will be less crack, or the crack section modifier or the stiffness modifier for the column is 0.7, means some moment can be transferred from less stiffer member to high stiffer member. In this case, this one is slab, this one is beam, and this one is column. So some moment can be transferred from slab to beam and beam to column because the stiffer member attracts more force. So by considering this crack section, the section and reinforcement demand may be high than using the uncracked section. We know that cracking occurs in the concrete when the tensile force within the concrete member exceeds the tensile capacity. So this crack is unavoidable in reinforced concrete member structure as well as masonry structure. The presence of these cracks complicates the determination of stiffness, which is in the terms of flexural, torsional, or axial stiffness. of a RC member. Accordingly, certain specified assumptions are made for the estimation of crack stiffness. A rational analysis is recommended, but in the absence of such rational analysis, the code mentions the stiffness modifier or the crack section value as these values. In general, the concrete is very good in compression as compared to tension. So about 6 to 10% of the compressive load is taken as a tensile load by the concrete. Whereas if we look into the reinforcement bar, which is very good in tension. So yeah, yeah. For example, suppose for a beam, suppose this is a simply supported beam, and if a load is applied on the beam deflect like this. Sorry, like this. Suppose this is a simply supported beam and the external force is applied in the beam and the beam deflects like this on the application of force. Sorry, yeah. Making the top fiber compress. Suppose this is a neutral axis somewhere here, making the stress diagram like this, which this one is in compression and this one is in tension. And the concrete fiber above the neutral axis tend to compress and the compressive load can be taken by the concrete as well. But below the neutral axis, the concrete fiber are in tension and the concrete fiber begin to crack because concrete cannot take the tensile force. So after cracking this concrete, the gross stiffness is reduced and mm, to consider this reduced stiffness, the stiffness modifier are incorporated in the analysis. So due to this crack moment of inertia, the moment of inertia of this beam is lesser than the gross moment of inertia. Hence, to account for the reduced moment of inertia, stiffness modifier are introduced, and different codes provide modifier to account for this cracking of concrete, which are called stiffness modifier. So stiffness modifier are the factors to increase or decrease the properties of the cross section. Generally, they are used to reduce or decrease the stiffness properties of the concrete section to model the crack behavior of the concrete, and they are applied only to the concrete member because it cracks under loading. We know that concrete is very weak in tension. The stiffness is reduced due to cracking, which in turn increase the deflection and the force. So these things will be incorporated in the analysis in ETABS. So by considering these crack sections in the analysis, it can be ensured that the sections are larger or safer, having 100% stiffness to keep the structure safe in terms of serviceability under the loading condition. It means that if the gross sections are used, uh, the sections are smaller than the sections while doing analysis with this stiffness modifier. And the low stiffness can cause the structure to deflect more with the given load, and it can be caused by using the flexible materials, smaller section size, and insufficient cross-sectional area. Therefore, the less stiff structure will deflect more force and experience higher deformation, leading to damage of the structure or failure. And if the deflection exceeds the put allowable limit. So different codes have different allowable limit for drift. For example, for in NBC code, we have the limit of 0.025. So here, okay, the ratio of inter-story deflection to the corresponding story height shall not exceed 0.025 for the ultimate limit state and 0.006 for the serviceability limit state. So this deflection shall be used by using the effective stiffness properties. So while doing analysis with the consideration of above mentioned stiffness properties in the ETABS, the obtained inter-story drift or inter-story deflection shall not exceed the allowable limit as mentioned in the code. Similarly, different code have different limits of inter-story drift in NBC 105, 2.5% for the ultimate limit state and 0.6% for serviceability limit state. So looking into the commentary of NBC 105 for drift and displacement, the deformation of the structure should be computed using the assumption that its members are highly stressed just prior to onset of yielding. Any rational method that includes all significant parameters contributing to deformation such as extent of cracking in the RC frame members, deformation of the joints and the cracking of cover concrete in the concrete encased structural steel frames may be used. While when allowing for effect of displacement, it is necessary to estimate the likely deformation during the design earthquake for appropriate limit state. So the displacement in the design earthquake can be estimated by multiplying those determined for the structure when subjected to the design lateral loading by ductility factor for ultimate limit state, and for the serviceability limit state the displacement is equal to the displacement that is calculated from the structural analysis or ETABS, here ETABS value. So for the ultimate limit state, while doing analysis in ETABS, the obtained inter-story drift or displacement shall be multiplied by ductility factor, so, which is mentioned in NBC 105-2020, and it is different for different structural systems. So if we go into the ductility factors, so let me go to NBC 105-2020. So this can be, or this value can be divided by the ductility factor in order to be consistent with the analysis in ETABS. So let me turn into the ductility factor here. Okay. So the ductility factor is 4. uh, 4 in terms of RC moment resisting frame. The resistance factor is 1.25 for ultimate limit state and 1.5 for ultimate limit state and 1.25 for serviceability limit state for reinforced concrete moment resisting frame. Okay, after this, let me turn into the tabs. Okay, here this is the ETABS model. Everything has a model in the ETABS. So the beam sections is 230 by 355 and the column section 350 by 350. Here there are two options for assigning the stiffness modifier in ETABS. The first one is go to define section properties, frame sections. Let me select the column and go to modify or show property. Here we can see the property modifier tag, and from here we can change the stiffness modifier. Suppose for example if we put 0.7 for column as indicated in NBC 105, here while doing while selecting or while displaying the information, we cannot see any modifier because we are assigning in the material properties. So if we select this column. If we select this column and assign, for example, frame stiffness modifier, for example 0.7 for column, then we see the property modifier here assigned in the column. Here we can clearly see that I22 and I33, it means cross moment of inertia is reduced by 30%, which is presenting or existing 70% of cross stiffness. That can be used for the serviceability limit state check of the structure, but not for the analysis and design. So it is better to use the property modifier with this second option by selecting the frames and assigning the properties. But don't do mistake by selecting the section and assigning the property as well as defining the section. Don't assign the stiffness modifier in two places, because if we put the stiffness modifier in two places, for example, the first one is also 0.7 for column, and in second option there is also 0.7 by assigning the material. So the modifier, let me go to calculator, 0.7 in section and again 0.7 in, sorry, 0.7 in defining the properties and 0.7 in again in the section. It comes the modifier of 0.49. So try to avoid this. You must avoid the using of modifier in two places. It is better to uh, use the modifier by selecting the frames and assign the modifier. So by selecting the frame, let me go to select properties, frame sections. Let me go to columns. Here all the columns have been selected, and go to assign frame modifier, property modifier, and here 0.7 for along the two axis and 0.7 for along the y axis or three axis. Okay, so by this way the property modifier assignment can be seen, and if we click we can clearly see that the modifier of 0.7 have been assigned. And going to section, frame section, we have to keep that value as cross. No need to modify in both places. Okay, so again I select beams, beams, sorry, beams, go to assign frame, property modifier 0.35 along two axis and 0.35 along y axis, three axis, which is indicated here in NBC 1052020. Okay, 0.35 for beam, 0.7 for column, 0.5 and 0.8 for crack and uncracked section of wall. So there are no any property modifier for the slab. So by this way, the property modifier or stiffness modifier of the structural section can be assigned in order to check the serviceability limit state, not to analyze and design by considering the crack section in the linear static analysis, linear analysis or elastic analysis. So I will compare the deflection, or I'll compare the value with the stiffness modifier and without the stiffness modifier or gross stiffness modifier. So let me select frame section, beam, the beam assign. I will keep as gross. Okay. Then again, let me select column, keep as gross. and I already defined the load patterns, earthquake in X and Y directions. So let me run this and let me save as to another one, stiffness modifier. Okay, I will open both of them and run parallelly, and we will check the response of the structure. Okay, so again, let me go to the test model here with gross stiffness. Okay, so the first one is for stiffness modifier, and oh, same. So let me open another one. So we open the another one, gross stiffness. Okay, so this first one is with gross stiffness, and this second one is with stiffness modifier. Then, if I run the analysis with gross stiffness and with stiffness modifier, so let me first confirm with the stiffness properties. Let me check this. So no any stiffness properties, and here with the section properties 0.35. Okay, this one is the model with gross stiffness, and let me select frame section, columns, assign frame property modifier as 0.7 and 0.7 along 2 and 3 axis. Similarly, let me select the main beam and secondary beam 0.35 and 0.35 for beam. So if we click here, we see clearly the property assignment of 0.35 along X and Y axis, or along 2 or 3 axis for the beams and column elements. So let me run this both model. So I'll run analyze set load cases to run. Yeah, no need to run nonlinear load case because I have set up nonlinear load case also. Okay, so run for this model also analyze set load cases to run nonlinear gravity not run, but sex not run. Okay, so let me run the analysis. Okay, the model has been already analyzed. So let me check the deflection. Suppose in the gross stiffness model, display story response plot. Let me go for earthquake in X direction. Again, display story response plot in X direction. Okay. So the maximum story displacement in the model with stiffness modifier is 0.043 meter, whereas in case of the model with gross stiffness, the maximum story displacement is 0.025, which means 0.043 is greater than 0.025 meter, because this is for the this displacement is for the structure with gross stiffness modifier, and this displacement is for the maximum displacement is for the structure with assigning the stiffness modification factor. So this drift or displacement or drift criteria should be satisfied in case of stiffness modification factor with the limit state of serviceability, to consider the limit state of serviceability. So if we look into the drift, okay, maximum story drift, yeah, maximum story drift, yeah, 0.003043 for the model with gross stiffness and 0.005093 with the model with stiffness modifier. Because in this model, the crack moment of inertia is considered for the analysis, and due to the crack moment of inertia, the stiffness of the structure is decreased and the displacement is increased, or interstory drift is increased. So if we see the stiffness for both model, okay, the maximum stiffness is at the study 1 with a value of 85,404 for gross stiffness and 56,657 for the model with modified stiffness. So this is the model with low stiffness value. That's why the deflection is more. Similarly, if we look into the forces, so let me go to element forces, display force stress diagram, frame fire link force. Suppose let me go for moment with the value, suppose, okay, yeah, and again display force stress diagram, file moment force, same, okay, yeah, oh, yeah, the first is the first model is the moment with cross stiffness, and second one is the model with stiffness modifier. Here, if looking into the beam, here the moment of inertia is decreased to 35% for the beam, and this is the moment of inertia with 100%. So we see that the gross moment of inertia is more, the moment is more with the model with gross moment of inertia because it is less stiff. It is the stiffness is reduced and the less force is attracted by this section, and it is transferred to the columns with the concept of moment redistribution method. Here, the moment is 8.934 kilonewton meter in the case of with stiffness modifier, but in the case of stiffness modifier, the moment is 9.72, which means it has high stiffness value as compared to this value, and it attracts more moment. So looking into the column, the moment is low because they all have uniform cross section and the force distribution is uniform, which means the column has low force demand in gross stiffness section as compared to the stiffness modifier section, and the column is designed for this value, and here looking into this section, the column is designed for higher value. So this is all about the stiffness modifier with a gross stiffness. So in summary, the model with gross stiffness, the beam attracts more force because with the full stiffness utilization, and looking into the column is more stiffer and less stiffer because it is a cross section and attracts less force. But looking into the model with stiffness modifier, the beam is reduced, the stiffness of the beams and columns are reduced, but the column's stiffness is reduced only by 30% and the beam's stiffness reduced by 65%. So the moment is distributed to the columns, and because the columns is more stiffer than that of beam, or we can say that column attracts more force because it is more stiff as compared to the beam, showing the higher value as compared to the model with cross stiffness. So this is how the stiffness modifier can be applied to the structure for the analysis. So today I can stop from here. In the upcoming videos, we will discuss more about the structural properties as well as the response of the structure. Till then, please like, comment, share, and subscribe my YouTube channel. Thank you very much.